Welcome to section 2.4. In this section, we look at dividing cash flows within a year and dividing discount rates within a year. Let me give you an idea what I mean by that. You get this, right? A fixed payment for 5 years at a, say, 8% discount rate. Well, here's the thing. Sometimes that 8% discount rate, that 8% annual percentage rate, is split into two 4% rates that are paying every 6 months, or that the payment stream is being split up into two payments every 6 months. That's called semi-annual compounding. Everything you've looked to at this point has been annual compounding. So we've left this difficulty off the table, but now we bring it in. Sometimes we have semi-annual compounding. And sometimes we have quarterly compounding. In quarterly compounding, you think of 4 payments a year. You can think of 2% each quarter. But there's no reason to stop at quarterly. We could go to any amount we want. In fact, we can go all the way to continuous. So maybe you have annually, semi-annually, quarterly, monthly, daily. Well beyond daily, there could be continuous compounding, a continuous stream of income. I know it seems theoretical, and yet it's used in finance. All right, this you know and you know well. Look, I got 5 payments in years 1, 2, 3, 4, and 5. Multiply each times their appropriate discount factor. 1 year, 2 year, 3 year, 4 year, 5 year, add them up. That's gonna get me present value. No problem. What's actually going on under the surface, I've never asked you to have to think about, but let me show you. This is what's really going on under the surface. It's really the cash flow in each of the years times a discount factor that looks like this. 1 over 1 plus R over 1 to the first power, look at the second one. 1 over 1 plus R over 1 to the first power raised to the second power, and so on and so forth. Notice the difference. All of a sudden, there's inserted this R over 1, and that inner piece raised, the 1 plus R over 1 raised to the first power. Let's see if we can just detect the pattern, all right? Remember, this is for annual compounding, once a year. What if we have semi-annual compounding, twice a year? Well, then this formula is certainly not going to work. I think we can tell right off the bat that's certainly not going to work. We have to have some modification. So what's the proper modification? Here it is. The discount factor is now, let's say for the first year, 1 over 1 plus R over 2 raised to the second power to the first power. We'll go over to year 5. Let's see what it looks like. The discount factor in year 5 is 1 over 1 plus R over 2 to the second power raised to the 5th power. So are you seeing the difference? Here you've got this R over 2 and you're raising it to the second power before you raise it to the 5th power. This is really what's been going on all along, but because we've been doing annual compounding, we've had ones and they've been irrelevant, right? All right, you think this is gonna work? No, absolutely not. We're down to quarterly. It can't be this simple. But what should we write in there? Do you have a guess yet? Are you experiencing the pattern yet? Take a minute and try to write the pattern. All right, this is what you should have come up with. Let's say, look at the year 3 cash flow. The discount factor is now 1 over 1 plus R over 4 to the 4th power raised to the 3rd power. So are you seeing the pattern? It's always the addition of this concept of R over the number of compoundings in a year raised to the number of compoundings in that year. That's the additional fact. Let's look at another. What if we had this? What if we had so many compoundings, we called it an infinite number of compoundings? You would say, doesn't make any sense. Yeah, but you did this in calculus all the time and it exists in finance. So certainly this is not going to do it. We can straight away kill such a simple idea. So what do we need to write now? How are we going to write this? I really want you to take a second and see if you can think of the pattern. We knew the pattern now. You've seen it for annual. You've seen it for semi-annual or quarterly. What would it be for an infinite number of compoundings per year. Pause the video and try to write your best guess. All right, here it is. Wow, look at that. It's 1 over, the limit as m approaches infinity of 1 over r over m to the mth to the first. Or in year 5, it's the 1 over the limit as m approaches infinity of 1 plus r over m to the mth power to the 5th power. Again, the only difference between this and what you had learned for the annual is over the r, you put the number of compoundings in that year, in this case m, and you raise that 1 plus that rate to the mth power. That's really what's been going on all along. You'd say, well, how come it's not r over infinity raised to infinity? Because that's the number of compoundings in a year. That's why we write the limit as m approaches infinity. You actually write m, you write the limit as m approaches infinity, and that effectively sends those two m's to infinity. You know that from calculus. All right. That seems like a lot to write and a lot to think about. So the good news is, embedded within these discount factors is the definition of the number e. The definition of the number e is the limit as m approaches infinity of 1 plus 1 over m to the mth. That's what e is. You may not have remembered that from pre-calculus or ever learned it. That is literally what the definition of the number e is. So you can replace the limit as m approaches infinity of 1 plus 1 over m to the m from every one of these discount factors with the number e. And so you're basically left with this very simple idea of 1 over e to the r to the first for the 1-year discount factor. Say, look at the 3-year discount factor, it'd be 1 over e to the r to the third. Wow, that's easy, isn't it? That's just happens to know, if you know the definition of e, it makes it a lot easier. And that's much more viable for using in a calculator, right? So learn the idea, which would be the limit language, and then learn what it converts to very easily through the definition of e, which is what people use in finance. All right, so let's revisit the formula. You know, when we had just an annual discount rate, an annual compounding, you just needed this formula. The discount factor was 1 over 1 plus r to the t for any particular year t's cash flow. No big deal. Annual discount rate r time t. But really what was always going on under the surface, and which will now allow you to adapt to whatever number of compoundings are happening in a year, is this. 1 over 1 plus r over m to the t, where we add this addition of m, the times compounded per year. Whew, I know. It's a whole other layer, but you're going to need it when you get to bonds, which is the next chapter. So if you hate the idea of a harder formula like this, you can always convert to an effective annual interest rate by using the equivalents. 1 plus r over m to the m equals 1 plus r effective annual interest rate. And then solving for r effective. What do I mean by that? You could, instead of using the bottom form, you could conceivably use the top formula if you convert the R that you're given, the annual percentage rate, to an effective annual interest rate. In other words, you're going from an annual rate that's going to be compounded, say, 4 times or 12 times, to an annual rate that is just compounded once. And you can do that using the formula on the bottom, which converts the interest rates from annual percentage rate compounding multiple times to an annual percentage rate only compounding once. Then you can use the top formula. Either way, you're doing the same thing. It's just kind of breaking apart the math. Know both of them. You need to know both of them because you're going to get a panoply of questions and you're going to have to be able to answer them using different ideas. So learn everything on this page. So here I just rewrite that formula that I just showed you, except I bring the 1 to the other side. So now it's R sub E, which is the effective annual interest rate, or the effective annual discount rate, is equal to 1 plus the annual percentage rate over the number of times compounded, raised the number of times compounded minus 1. Memorize this formula to convert, all right? What am I saying here? Very often banks, other institutions will quote to you an APR, an annual percentage rate, like 12% APR paid monthly. And all that the average consumer hears is 12% APR. That's my interest rate. But if it's paid monthly, it's not just like having a 12% interest rate. There's compounding happening 12 times in the year, and that affects what the equivalent annual interest rate would be if it was paid annually, just once a year. So the way we can kind of compare apples to apples between various annual percentage rates at different compounding levels is first convert to an effective annual discount rate. The effective annual discount rate, R sub E, that's like what you've been looking at up till today. Everything up to today, that R is always an annual discount rate, just pure annual compounding, once a year. Okay, so this would be 12.68% APR paid annually. That's essentially what you're talking about. Now, I want you to know these two things are equivalent. 12% APR paid monthly is equivalent to 12.68% APR paid annually. So when you're getting a loan from a bank, or when someone's promising to pay you a fixed amount of interest, you need to know how often the thing is compounding. And unfortunately, most people in society can just understand 12% APR as a 12% interest rate. But they have no idea that a 12% APR paid monthly is different than a 12% APR paid annually. So if you can convert everything to annual, that is once a year rate, an effective annual discount rate, you can compare apples to apples across loans and across products that'll pay you a fixed income stream. I know it's a lot. Let's look at a problem here. An investment promises to pay you 10% per annum. You invest $1,000. How much will you have after 4 years? Okay, sounds straightforward enough, right? But that depends what is meant by 10% per year. Up until now, it just meant annual interest payment, right? Up till now, it has meant and most often will mean 10% paid once a year at the end of the year. But it could mean 5% paid twice a year at mid-year and at year end. Or it could mean 2.5% paid 4 times a year at the end of each of quarter 1, 2, 3, and 4. You need to look for clarifying details in the questions being asked of you. Now, if there are no clarifying details given, you can assume compounding annually. That is once a year at the end of the year. But if they give you clarifying details, you cannot ignore them. You must use them. Here's a good entry-level question. An investment pays 10% per year. You invest $1,000. How much will you have after 4 years if interest compounds annually? Or how much will you have after 4 years if interest compounds semi-annually, right? So this is essentially a future value calculation. All right, what do we say for annually? Pause it, see if you can do that calculation. You should be able to. All right, and we're back. All right, the future value calculation is going to be 1,000 times 1.1 to the 4th power, or 1464.10. I don't know why it says 1.01 there. Sorry, but it should be 1.1 to the 4th power. And if you're wondering, how do I know that that's what it's going to be? Well, first I converted it from an annual interest rate to an annual interest rate. In other words, there wasn't any conversion at all. How did I do that? I used the formula R effective equals the 1 plus the APR over the number of times compounding, raised the number of times compounding minus 1, which of course, since this is annual compounding, would be just like the original formula, it's just 1.1. What happens if you do semi-annual? You figure it out, then check. All right, now we got 1 plus 0.1 over 2 to the 2nd power minus 1, or 10.25%. This is semi-annual compounding. So this is now what we've just done, going from 10% being paid twice a year, like 5% for the first half of the year, 5% for the second half of the year. We've converted that to an annual interest rate. It'd be equivalent to paying 10.25% at the end of the year. And how do you do the future value calculation? It'd be 1,000 times 1025 raised to the 4th power. Again, the numbers are reversed here, I'm not sure. It should say 1.1025 to the 4th power. Notice, when you have annual compounding, your future value is 1464. For semi-annual compounding, your Future value is 1477. Does that make sense? The more times you compound, the more compound interest you will earn. Therefore, you should have more money at the end of 4 years. What if we go with monthly? Can you do the calculation? Pause it and try. And here's our calculation. Now, instead of dividing by 2 for semi-annual, we divide by 12 for monthly and raise to the 12th power. So once again, I'm converting from the APR, which is 10%, paid monthly, or 12 times a year. I'm converting to the effective annual interest rate, which would be the discount rate if I only had annual compounding once a year at the end of the year. I use that in my future value calculation. Look, again, the number's gone up, as you'd expect, to 1489. Again, that's written wrong. It should be 1,000 times 1.1047. Not sure what happened. Finally, we have continuous compounding. Now here, right, it would be R sub B equals the limit as m approaches infinity of 1 plus the 10% over m raised to the m minus 1. But I told you, because of the definition of E, that effectively converts to e to the m here, right? So e to the m minus 1, it should get you 10.52% effective annual rate. You're compounding more than 12 times, you'd expect a higher effective annual interest rate. And that equates to 1491.98. Now you would think with continuous compounding it would have gone through the roof. It doesn't. All right, there's a point at which things kind of slow down. Right, so much of math is seeing things, the same thing, multiple ways. And with this topic, you must look at the same thing multiple ways. So it looks like the numbers are correct on this slide, right? All the conversion numbers are right, 1.1025, 1.1047, everything's correct on this slide. Now, what if I didn't want to convert my APR, compounding semi-annually, to an effective annual interest rate before calculating future value? Could I calculate future value in one fell calculation? The answer is yes, you can. Let me show that to you. Here it is. It'd be 1,000 times 1 plus 10% over 2 to the second power to the fourth power. And right there you get 1464.10, which is not matching up with the 1477.46. I'm not sure what's going on in the slide. This is odd. Anyway, let's keep moving here. The numbers should match up. Okay, let's look at the monthly slide. They match there. There you go. So instead of converting our 10% to a compounding semi-annually to an effective annual interest rate of 10.47%, we can just go straight to the future value calculation, multiplying $1,000 times 1 plus 0.1 over 12 to the 12th to the fourth power, and get our 1489.35, right? And then continuously, once again, you don't actually have to convert to the effective annual interest rate of 10.52%. Instead, you can do the following. You can just go ahead and say future value is $1,000 times e to the 0.1, which is e to the r, raised to the fourth power, which is the number of years here. Okay, and you will get 1491.98, which is approximately what I got before. It's probably just when I did the calculation, got some rounding differences. Sorry about that first slide. I obviously just, it should be 147746, I believe. Yes, it should be 147746. I just wrote it wrong. All right, now we have to handle word problems with this stuff. An investment offers to pay you $100 per year in perpetuity. Normally that means the first payment of $100 begins 1 year from today. That's what you've seen up till today, right? However, the investment manager proposes not just the typical option, but 3 different options. Which would you choose? Assume a discount rate of 7%. So the first option is a perpetuity making annual payments with the first payment after 1 year. That's what you normally do. Then you have perpetuity making annual payments with the first payment today, right now at time 0. That's odd, right? Or perpetuity making continuous payments throughout each year and starting the continuous payments today. In other words, instead of paying at the end of the first year, which is a normal situation, or paying right now at time 0, which is odd, but it's talked about in your textbook, you could actually make the payments spread out, compounding continuously. Let's see what the math will look like for each one. Well, the first one you should be able to do pretty easily. Right, present value is going to be 100 times 1 over 0.07. No problem, you can do that. That's just a zero growth rate perpetuity, where the first payment's the beginning of year one, which should be the end of the first year. That's your standard situation. How about the second one? Well, the second one still has that same perpetuity, right? Starting a year from now, but it also is a payment today. Well, the payment today is in present value. So just add $100 to the calculation you just made. That will be a perpetuity making annual payments for the first payment today. Now, what about the perpetuity making continuous payments throughout each year and starting the continuous payments today? You want to try that? You should try it. I know it's probably going to be tough, but pause it, try it. All right, here you go. It's going to be 100 times 1 over the natural log of 1.07, which is 1478.01. You're like, where did you come up with the natural log of 1.07? We haven't even talked about that. Well, you know that the natural log is the inverse function to exponential base e, and you know that's in the continuous payment calculation. So maybe you can see it here into the bottom. I put it in red for you. The effective annual interest rate is going to be 1 plus that kind of annual APR discount rate of R sub A over the number of periods minus 1. Well, we said that when we take m to infinity, that looks like the effective interest rate, R sub E, is equal to e to the R sub A minus 1, right? Well, we can rearrange that to have 1 plus R sub E equaling e to the R sub A. And then we can apply the natural log function to both sides. You have to do that in calculus all the time. Now you know what's going to happen with the natural log of e to the R sub A. The natural log in the e are to cancel, leaving you with R sub A equals the natural log of 1 plus R sub E, right? So this is what we've effectively done here when we have natural log of 1.07. I know it might take looking at it a few times. All right, what can I say? I threw a whole lot of information at you really quickly. It's going to be a lot to take in. It's not going to be fun. It's not going to be intuitive, but you have to get this last element of discounted cash flow math underneath your belt before we get to bonds in the next chapter. Because bonds in the United States, they don't compound annually. They compound semi-annually, and it's different depending on what bond you're looking at. So, all right, watch the video 2 times if you have to. Have a good night.